Hello, everyone. Can you hear me? Good. So my name is Paul Schroeder. I'm a QA engineer at Rosetta Stone. A little bit about me. I've been in the QA industry for the past 8 years. I got my first testing job at Motorola and then moved to EchoStar. And I've been at Rosetta Stone for the past 3.5 years or so. You can feel free to follow me on my social media pages or my GitHub. So who is Rosetta Stone? I'm sure you guys have, many of you have seen Rosetta Stone yellow boxes before. We were founded in 1992, so we've been around for a long time. We're kind of a dinosaur in this industry. And we are a language and learning software company. You can find our products in schools, enterprises, and consumer home products. You can find our apps on the Play Store and the App Store. The consumer product is called Learning Languages, and this is our mission statement. We're dedicated to changing people's lives through the power of language and literacy education. So why does Rosetta Stone QA need to test speech? We have our own in-house speech recognition engine that can detect 40+ languages and dialects. 8 of those languages are endangered, meaning that we have less than 50 native speakers of those languages, so we try and preserve them through our products. Some examples of those are Chickasaw and Luiseno, both of which are Native American languages in the US. The speech recognition engine runs natively on web, iOS, and Android platforms. It's the same piece of code wrapped in different wrappers to be able to execute properly on those platforms. Another reason, or in addition to that, there are many permutations in speech. So speech is a non-binary thing to test. There's no one positive or one negative test case because we all have different vocal profiles. We all speak differently, we have different accents, we have different genders. Background noise can play into how speech is interpreted by software. So to start out, we can create some manual test cases that do test those binary examples. So for instance, you say one correct thing and you say one incorrect thing, and you expect the positive UI versus the negative UI. This can help us find regressions earlier in our software before it gets out to beta or even our manual testers. So you might say, that's good for Rosetta Stone, but how does that affect my company and the QA industry in general? Well, as you all know, all of our phones have speech recognition. We all have voice digital assistants. We have Siri, Alexa, Bixby, Cortana, Google Assistant, Currently, there are 2.5 billion in the world of those digital assistants, and by 2023, it's estimated there will be roughly 8 billion in the production market. So, how do we at Rosetta Stone assure quality? We use Jenkins. We follow a fairly common CD pipeline. CI/CD pipeline where a dev completes a feature or a bug fix. QA will test that specific branch. We will write any manual or automated test cases for that specific branch. And then we will merge that and any new tests into master, and Jenkins will run through the pipeline. You can see one of our pipelines here where we merge and master, commit stages are building. We deploy to a test environment, we run acceptance tests, we deploy to prod, we run a subset of those tests on production, and then we deploy to all of our non-prod environments. So in addition to Jenkins, some of our other tools that we use are Nightwatch.JS for Selenium. The reason we switched from RSpec to Nightwatch about 2 years ago. The reason being the simpler syntax made it much easier for people to start using automation. Manual testers could just jump right in and use that syntax, and there was less of a hurdle there. It's also easily extendable, so you can add custom commands, custom assertions, and use those widely throughout your test suite. It also has cool built-in CI features like parallelism, screenshot capturing, XML results, just built in. For our mobile Appium testing, we use an extension of Nightwatch by the TestArmada team called Nightwatch-Extra. Nightwatch-Extra is made, the TestArmada team is Walmart's test team, by the way, and a big shout out to them because that framework is really awesome and we've had good use of it. It uses the Nightwatch syntax to test native iOS and Android apps. For our web grids, we switched probably about 3 years ago to Docker, and probably about last year to Kubernetes. So we use Kubernetes now to schedule and manage those Docker containers within our Selenium web grids. The pros, basically the reason that we switched were that virtual machines were getting way too cumbersome to maintain over time. So now we just can spawn Selenium grids on the fly. They're easy to create, easy to destroy, and you don't have to maintain them like you would with a virtual machine. So now kind of the meat and potatoes of this. How can we play audio files within our Selenium tests? I found 2 methods to do this. The first one was Google's built-in Chrome arguments. So Google includes something called useFile for fake audio capture, and then you can append a WAV file to that it will play anytime that the microphone is attempted to be accessed, which is a really cool built-in feature. That use fake device for media stream argument is to suppress the dialogue that asks you permission to use the microphone, so that just suppresses that. So the pros to this are that it's very simple to implement within your framework, but there are a lot of cons in my opinion. You can only use 1 audio file per Chrome launch. So as you could see, equals mediafile.wav up there, that only includes 1 file. So you can't be calling multiple audio files within the same test. In addition to that, it can be checked and disabled by websites. An example of that is Google itself, who implements this feature, does not allow you to use this Chrome argument on their own Google search, Google voice search. In addition to that, Chrome might, in order to save bandwidth, might decrease the quality of that audio. And the biggest con of all might be that it works only in Chrome, doesn't work in other browsers. So that led me to method 2 here, and excuse my rudimentary drawings, mock-ups here. So imagine this is a PC tower. In a standard computer, you'd have a microphone that goes into the input, you'd have the headphones, and the speakers go out from the output. So imagine if you took an auxiliary cable and you plugged it into the output side, and you directly just plugged it into the microphone input, so that any audio file that you played would come back in as input, as if somebody was speaking it into the microphone. There are a lot of pros to this solution, in my opinion. You can use any number of audio files within your test. So if you had 5 or 10 audio files that you needed to play in succession within one test, you could. It fools the computer at a hardware level rather than a browser level. So this is a layer deeper than the first method that I showed. The audio input is processed as raw, so you don't have to worry about down conversions that the browser could do. It's simple to set up on a real machine, as I showed with the auxiliary cable. There are also little USB devices that allow you to route audio that way. And it can work in Chrome or Firefox, or essentially any browser that allows you to suppress that media pop-up within tests. At the moment, that's only Chrome and Firefox, to my knowledge. But if Safari ever added it to their driver, you'd have access to this there as well. So the cons are that it's somewhat difficult to set up on virtual machines. You need to download some external software, open source software. And it was also difficult to set up in containers until, I think, this implementation. So how do we Dockerize that method? So we can just extend the standard Selenium headquarters Docker images. Doing this on your own would just kind of complicate things. Really what we want to do is just inject some code into the standard Selenium HQ node images so that they use their audio drivers in this way. So it can work with a grid node or the standalone Selenium images. The second tool that we use for this is Pulse Audio. So Pulse Audio is a Linux open source audio proxy that sits between the hardware and the software of a Linux machine. It allows you to manipulate the drivers. It also allows you to fake input and output devices, which is what we need in terms of containers because they don't have real hardware. So we need to fake these input and output devices. In addition to that, and this was kind of an optional thing that I wound up doing, but we set up a simple HTTP server inside of the containers that host the audio files that you've recorded and placed in there. You could also, if you were to store these audio files on some external server, somewhere.org/media files, you could just call them from there as well. So that last part really isn't necessary, but I found it very helpful because it cuts down the latency between calling an external server for your audio files. It has to, cache that file and download it, reach out to the server, whereas putting it at localhost means it's there. It doesn't really need to reach out to the internet. So what would the Docker file look like for a project like this? Like I said before, we're going to inherit the Node Chrome debug images. That's the latest Pi version of it. As root, we're going to install a few dependencies. Pulse Audio, like I was just talking about, the audio manipulation. PavView Control, which is a UI that allows you to kind of see what Pulse Audio is doing, which is really nice for debugging and in getting all this set up. So I left it in there in case people want to see how this is working in a UI type fashion. And additionally, Python, like I said, for that simple HTTP server that we're going to host inside of the containers. The next step that we do in this Docker file is we make a folder called OpMedia, and we copy anything inside of the media folder. You can see that count15 mail.wave there. That's an audio file. We copy that into the container at OpMedia. And then we finally copy this entry-point.sh file into the container and run it as Selenium user at the end. So now we have our dependencies inside of the container. Now we need to configure them. And that's where the entry-point.sh file comes in. So we're going to load Pulse Audio. This is the entry-point.sh that we call from the Docker file. We're going to create our virtual speaker and virtual microphone. And then we're going to stand up our simple HTTP server here from within the OpMedia folder. So anything that lives within your media folder will get hosted at OpMedia. And then the final thing we do here in the entry-point.sh is we call the standard Selenium Chrome node entry-point.sh. So Selenium HQ's version of their entry-point script. So that way, that's what starts the Selenium server, that's what starts VNC and the debug images, etc. So let's say you want to record files and put them into your Docker container. What can you use to play these files, or record these files, sorry. I use Audacity, but essentially any wave recording is going to work. Any wave recording software, sorry. So this is me speaking the word businessman into this recorder. And then I'm going to export it as a WAV file. And again, Audacity's free, open source. I'm saving it here as businessman mail.wave. And you know what, let me full screen that because it's probably hard to see. Well, for the next one I will. But we saved it as a WAV file. And you can see I've added it to the media folder here. Inside the container. So we want to add this to the Docker image so that anytime that the Docker container gets created, we have access to this businessman mail.wave file. So you would copy the file into the media folder, you would build a new Docker image of this, and then you could run it via this command down here. And I'll get more into running in this slide. So in running the Docker image, this is for a grid setup. So if you're using grid, you want to create a network. In this case, I'm calling it grid. We're going to run a hub on port 4444, and we're going to run a Selenium Chrome node with audio looping. Sorry for the mouthful. We're going to run that image on port 5900 via these commands. And with 5900, if you are not familiar with Docker Selenium, that's for VNCing in, so you can actually see what's going on in your tests as you're running them. So now we're VNC'd into the container, or we will be. We're running the container here. And I'm opening up VNC. Now we're in this container. And I'm going to go to that localhost 8000 just to verify that the files are now there. And as you can see, that new businessman mail.wave is now in there. So now we want to call these audio files from within our tests. And the best way to do that is using Selenium's JavaScript executor. So this comes bundled in with Selenium. If you're not familiar with using it, it has two exposed methods, execute script and execute async script. Execute script is for running a piece of synchronous code. That's really not what we want here. A synchronous piece of code would just fire off the command to play an audio file and never wait for it to complete. So it would just move on to the rest of your tests. Execute async script, on the other hand, allows you to expect a callback, and that will allow you to wait for the audio file to complete playing before moving on to the next step. So here's the code in Nightwatch.js. If you're not familiar with Nightwatch, I'm going to jump to Ruby code next if you're more familiar with that. But this is a custom command I've created called speak into microphone. You would name the file speak into microphone.js. You'd put it into your custom commands folder. And we're calling this .execute async. So again, the execute async JavaScript. And the relevant code here is here. From const audio to audio.play. That's the code that we're injecting into the browser. And that's going to construct a variable called audio. It's going to assign a URL to the source of that object to know what to play. And then it's going to add this event listener of ended, which says run done once the event listener has been reached. So once it's ended, then you're done. That's what that means, and that's why the execute async is so important. And at the end here, we play the audio, which waits for the event listener. So in Nightwatch, you can just call this method, this custom command via browser.speakintomicrophone, wavefile.wave. If you want to call from an external location, though, you could just include it as a secondary argument here. You can see the first argument is wave file name. The second argument is predefined as localhost, but you can override that. So this is the Ruby code, the RSpec code. We're going to define a method called speak into mic. Same deal. We're going to pass in an argument of wave file name, optional argument of server, whereas by default it's localhost 8000. And here's the syntax in Ruby. This JavaScript code is essentially the same, where we add the event listener. And that's the code in Ruby. So to get this working, really the only argument you need to include in your desired capabilities is use fake UI for media stream. And I know I said it previously, but that is to suppress the allow microphone pop-up, because that can't really be clicked, to my knowledge, from Selenium itself. I think that's on the browser level. But your Nightwatch test will look something like this. You would define wave file name as whatever you want it to be, whatever is living inside of your container. Right here, it's businessman mail.wave. We're going to go to Google. We are going to Click on the voice search button. We are going to wait for Google Audio recording to be ready because that takes a slight delay. And we're going to speak into the microphone, and then we're going to assert that the title is now that voice search term. Before you guys all come at me after this, I know that this isn't following best practices, and I have a hard-coded sleep in here, but I was just doing that for the brevity of this. I didn't want to start making page objects. So running the test would look like this. So we're back VNC'd into this container. We're at Google, we click the voice search, we're waiting. And we spoke businessman. And now we're waiting for businessman title to be in the top, and we're waiting for that hard code sleep to be done. So yeah, and also if you're not familiar with Nightwatch, if you haven't seen it before, this is what the output looks like. This is another reason that I really like it, in that you can pass these test results off to people that are less inclined to understand your test, but they'll understand what your test did. So how do we take this and leverage it at Rosetta Stone? So earlier I said, at first, we could just create positive and negative test cases where we just send the right file and then the wrong file and verify that the UI changes accordingly. In the future, I can see us getting enough samples throughout our company, throughout our users, where we can run different samples through these same positive and negative test cases as well, just to have more data on it. So this is what a negative test case would look like. And that would be the end of it. And I've slowed this test down considerably. So I'm sorry if it's too slow, but I've slowed it down intentionally with sleeps just to make sure things don't breeze by too fast. So this is our enterprise product known as Catalyst. And we're going to launch a product that's in beta right now called Fluency Builder. This guy right here. And we're looking to ship this by the end of this year, I believe. So these are the courses that the user has assigned, and all the UI is not completely done yet. So in this particular thing, it's called vocabulary. We have all these words that the user is expected to listen to and then speak. So in this test, what I'm going to do is I'm going to click on listen, and that audio file played. And then I'm going to click the record button, and I'm going to send intentionally the wrong audio file and make sure that the incorrect UI shows up. There you go. So you can see down here in the logs, and I think I jumped to it in this video, but we played businessman mail instead of to centralize as the search term, or as the vocab term, sorry. And let's do that with a positive test case. And with this one, I'll hop around a bit because it's essentially the same until the end. So we're here at the courses again. And we played listen, and now we're going to pass into centralize. And we're verifying that the correct UI is there. So this opens up a lot of doors for us at Rosetta Stone because previously we could only test the negative test cases. So we could never fully realistically get to the end of an activity where there was actually speech because you could only ever verify the negative UI. So if you're not using Docker Selenium, that's fine. You can still use this implementation if you're using virtual machines or if you're using Windows or Mac real hardware. You would just download these tools. Soundflower for Mac, VB Cable by VB Audio for Windows. I haven't personally tried VB Cable, but I read that it does essentially what Soundflower does and what Pulse Audio does in the Docker containers. So what's next? What ideas do I have next for this? I would love to see this working for native mobile apps. We have, like I showed earlier, we are using Nightwatch-Extra by the TestArmada team, and the biggest setback would be that there is no browser instantiation in an Appium test, an Appium native test. So we can't run execute async script because that's what we run in the browser. So my thoughts are somewhere around using SSH calls to play the audio files off of a media server that live on the Mac or Windows machine. But if you guys have any better ideas than that, let me know. And then additionally, I'd like to see us use this with machine learning to help make our, let me hide this, to help make our speech recognition engine, sorry guys. To help make our speech recognition engine better. And in doing that, we would just have to feed it thousands and thousands of audio files. I've been reading up on audio simulation recently where they have like these synthesized voices that come out very realistically. I'm not sure if that would work, but it would be really cool to try out. So if you want to collaborate on this or any of the other things that I work on, feel free to check out the GitHub repo for this and the Docker Hub repo. The README in the GitHub repo is just as detailed as all of this. So all the code snippets and everything are available in there. And with that, I will open the floor for any questions. Sorry. Thank you.
Thank you all. Do you have any question, please? Oh, okay. Wait, please. Sorry, we are preparing mic soon. Mic, please.
Hi, so my question is, this is cool for recording the voice when you have voice recorded like in Google, for example, but that sounds a little bit robotic. I have a lot of issues with, as you can tell, I have an accent, so I have a lot of issues with voice apps, and I was wondering how you can use this and deal with accents and things like this.
Yeah, so at first, like I said, we are just trying to do the positive and negative test cases for each one, so just sending intentionally the wrong file, the wrong audio. But at some point, I would like to see it where our QA engineers could rely on public recordings of people speaking and feed it into our speech recognition engine. That would hopefully make it better in the long run for people with accents or any type of difference in their voice.
That's cool, thank you.
Another question?
Yeah, because the developers which are working on this, the core of the engine, how do you, what are your test difference from the, for example, the unit test or the components test, which they are executing? Because I can imagine there will be some overlap, or they have some.
Yeah, there is definitely going to be overlap there, and we do have a robust amount of unit tests and integration tests, but because speech just has so many permutations, there's just so many differences in everything that we say and do, and the way we speak, the spacing between our words, that the more data, the better. And having something like this is really nice because we can test it on the client side rather than just the unit tests of the application itself, the speech recognition itself. The additional benefit of that is if there was a poor implementation by some of our app developers who take this speech recognition and put it into the app the wrong way, for instance, we can catch that where they wouldn't with their unit tests.
Okay, thank you.
Thank you.
Does anyone have other question? Okay.
Well, great. I will be walking around this afternoon and tomorrow. If you guys see me in the hall and want to ask anything else, if anything comes to mind, just let me know. Thank you very much.
Yeah.
Arigato.
Thank you very much.